Review of Chapter 2, 3, and 5. Today we will review the concepts in Chapter 2, 3, and 5. For specific problems, you can go over the old exam problems and the practice exam problems in the website. So we'll just go over the formulas. So Chapter 2, first order equation. There are three types. One is linear equation. You can solve it using quite a few different methods, but here we will use the approach of integrating factor. So if we can integrate p and get this mu of x, then we can multiply mu on both sides, and we'll see the left-hand side becomes mu y prime, the right-hand side becomes mu g. Then we can see y just given by this formula. Right, so that's how you solve the linear equation. Second type, separable. If the equation can be written as y prime equals a function of x times a function of y, then you can just write on dy over g equals dx times f, then integrate, right? But a particular case is so-called homogeneous equation. For example, it's something like that. The top, the numerator and the denominator are functions of x and y, polynomials of x and y of the same order. When I say same, I mean you add up to the order. So 2 plus 1 is same as 3. So to solve that equation, you first divide the numerator and the denominator by the x to the common power. You get 1 plus y over x cubed. Then this becomes y over x. Right? So you can see everything becomes a function of y over x. So we will let y over x be p. Then y equals px, so y prime equals p plus p prime x. And then you can see it equals 1 plus p cubed over p. So you can move p to the other side. So you can see p prime is a function of p divided by x, so it's separable. Then you can solve for p. Then once you get p, you can multiply by x to recover y. Right? That's how do we solve the homogeneous equation. And the third type is the exact equation. If the equation is written in this form, and we can check the partial derivative of m with respect to y, and the partial derivative of n with respect to x. If they happen to be the same, then we can call this equation exact. And that implies there exists a function phi whose x derivative equals m, and y derivative equals n. How do you construct phi? You can just integrate m with respect to x with y fixed, but that's not determined completely. You have to add an arbitrary function of y, and this h is to be determined using the second equation. Once you determine this h, you can say you know what is phi, so the solution would be phi xy equal to constant, and the constant can be determined by the initial condition. Okay, and in the case that it's not equal and it's not exact, then we can find out integrating factor in certain cases. But let's say for this final, we don't need to worry about that. Let's only worry about the exact case. Okay, but you have to verify it is exact before you use this method. Okay. All right, let's go to the second part, the second order equation. Second order linear equation. Okay, if it's linear equation, then it can be written in this form. And how do we solve that? We do it in two steps. First, solve the homogeneous one. then find a particular solution to the non-homogeneous one, then add up the solution to the homogeneous one, you get the total, general solution, right? However, even the linear homogeneous equation is not always easy to solve. In general, we don't know the solution, but for a special case that P and Q are constants, we know how to solve, we know how to solve the equation, right? We can let y be e to the lambda x, then plug in, you will get lambda squared plus a lambda plus b times e to the lambda x equals 0. Then you can cancel that. You get two solutions for the quadratic equation. So you get lambda 1 and now lambda 2. So you get two linearly independent solutions. And if lambda 1 happen to be equal to lambda 2, then it would be e to the lambda x and e to the lambda x times x. Right? And if they are complex numbers, then you can write down the real part and the imaginary part. And the imaginary part in the exponential function will become sine and cosine. Okay. And the other special case is the Euler equation. And for this one, you let y be x to the r, a power function. Then you have x to the r minus 1 plus ar plus b equals 0. And cancel that. You solve for r, you get two solutions, x to the r1, x to the r2. That's your y1 and y2. Okay, very similar. And if r1 equals r2, then instead of times x, you times log x. All right, now let's go back to our general equation. In general, you don't know the solution, but if you somehow guess or you're given a solution y1, then we can use the Wronskian method to find out the other solution. The Wronskian is e to negative p, like that. You could have a constant in the front, but if we just want to find out a solution, we can just assume that constant is 1, so you can just erase that. Then you can use y2 equals y1 times Wronskian over y1 squared to find out the other solution. Okay, the other linearly independent solution. Okay, that's it for the homogeneous equation. For the non-homogeneous equation, you want to find out a capital Y from your G on the right-hand side, right? If your equation happen to be y double prime plus ay plus b equals this G is a combination of sine, cosine, exponential function, power function, then we can use this as a undetermined coefficient method. You write down all the G and all its derivatives, and G prime, G double prime, etc. Provided this is in a finite pool, right? If it does not repeat, then you cannot use this method. And when you write down that, you have a lot of terms and with undetermined coefficients. And there's some special cases that you have to multiply by x or sometimes even x squared. That is, if your G happen to be a solution of the homogeneous equation, then G itself wouldn't work. That's why you have to multiply by x. And if G times x is still a solution to the homogeneous equation, then you have to times by x squared. All right, you can see more examples in the practice sheet or just in the old exams, the previous exams. Okay, last but not least, there is a formula when you cannot use this undetermined coefficient method. If you happen to know y, or you have to find out y1, y2 before you do this. If you know y1, y2, then you can always find out your general solution using this formula. G over W plus y2 y1 G over W. And remember, this W is not just that. Because if you do this, then you don't know what to see. That's not correct. You should use y1, y2 prime minus y1 prime, y2. So you can compute this W with the particular choice of C. Okay, but in general, this integration could be hard. So you don't use integral unless you have to. Okay. All right, that's it for chapter 2. Chapter 3. Chapter 5 is power series solutions. Suppose you have a second order equation like that. And this PQR are smooth functions, but usually they are polynomials. If we happen to have a point x0 where px is non-zero, then we can say x0 is an ordinary point. So you can use power series solution. You can let y be summation of an x minus x0 to the nth. Well, usually x0 is 0, but not necessarily. And you plug in this one into, take its derivative, and second derivative, and you do the shift of the index if needed, so that you can always have nth power in all these terms. And sometimes you have to split the first term into 2 terms or second term, etc. Right? Until you get all the powers matched up. Then you get the recurrence relation between A0, A1, A2, etc. For example, sometimes you say A0 will determine A2, and then determine A4, etc. A1 will determine A3, A5, etc. So then you will see the solution can be written as A0 times a solution we call Y1, and A1 times the solution called Y2, and A0 and A1 serve as a C1, C2 in our usual case. Okay, and if P of x0 happen to be 0, then it's a singular point. And how do you deal with a singular point? You check if you have a finite limit of this one and the other one. If you happen to have a finite limit in both limits, then you can say it's a regular singular point. And that's good, because we can still use power series, provided you first solve the Euler equation. And the Euler equation would just be x minus x0 squared plus a plus b. You solve that, you will get r1, r2. So your solution would be x minus x0 r1, x minus x0 r2, like that, right? That's your y1, y2. But that's for the limit equation. This is in a limit. And to solve the original equation for PQR, you can multiply a power series solution to 1 or both of them. If R1 minus R2 is not, okay, we always choose R1 to be more than R2 or equal to. So if the difference is not an integer, then both y1 and y2 can be found. You just set y to be x minus x0. Let's say x0 equals 0. Okay, just because that's the usual case. So you can just say x to the r, then sum of a and x to the n. Then you solve it. You plug in this to the equation. Then finally you let r be r1 or r2. So you get 2 independent solutions. One for r1 and the other one for R2. But if the difference is an integer, which means 0, 1, 2, etc., then y1 can be found, but y2 may not, because y2 may not, typically y2 is not in that form anymore. It will involve some logarithm function times y1. So we will not try to find our y2. But if you want, you can find our y2 using the Wronski method. But we won't do that. We will just find our y1. That's it. Okay. And I think that's it for this review. So you just go over the previous exams and the practice final online. And the practice final come with the solution. So you can just check if you got it correct. And then we will have the exam. All right. That's it for this semester, and have good luck and stay healthy.